Okay, hey everybody, welcome to Control System Analysis. We're going to take this transfer function and we're going to draw the Bode plots for it. Hopefully you've watched the introduction video, so you're not going into this cold fish, but if you're just looking for a Bode plot example, then hopefully this one will help you out a little bit. So the first thing we're going to start out with is just kind of getting some general information from this. Well, we see that we have a pole at the origin, so we know that I'm going to go ahead and put the magnitude right here, and then the phase plot here. Phase plot right here, magnitude right there. Just some general information. So for the magnitude, we're going to have some initial value that's not 0 because of this origin point. So it's not at 0, not at 0, 0. We also know that we're going to have probably a total downward angle of like -40 degrees at the end of it all, or 40 dB per deck, because we have one pole which which adds 20, and then these poles which subtract 60 because each one of them has a dB per deck of -20. And then for the phase, for that same reason, zeros contribute 90 degrees, poles contribute -90 degrees, so that cancels out to -180 degrees. So that's where the phase should end. Just some information there. And since we have a pole at 0, we know that it's a pole at the origin. We know it's a type 1. And that's about all the general information and kind of heads-up info that we can get. So the first thing we want to do, especially with the magnitude, is find out what the initial value is in decibels. So what you do for that is you basically take S and either take it to 0 or take it to a really small value. Basically, S goes to the original omega. Well, in our table, since we're dealing with 1, the lowest value we'll deal with is 0.1, and you'll see why in the magnitude in the phase plot that we do in a little bit. So omega naught is basically going to go to 0.1 or 0. You can call it whichever. But if you reduce this transfer function will go to 3 over omega naught, we're calling it omega naught for now, times 2, which is 2 times 1 times omega naught, basically. And then, if omega naught is 0.1, then this will equal 15, which is unitless at this point, but in order to turn it into decibels, the original set of decibels for our magnitude plot over here, this is going to basically be, go ahead and take 20 log 10 of 15, and this will equal 23.22 dB. And this is just the translation between the degrees or the units and decibels. So if you're curious about that, you should know this conversion. So for our magnitude plot, we're starting at 23.3. Okay, so let me get that set up over here. This shouldn't be too bad. I'm going to go ahead and put 23.3 up here, just for the sake of simplicity. This is going to be 0. This is going to be 20, actually. I'm going to put 23.3 like right about there. And you'll see why I'm choosing a distribution of 20 right here, because since poles and zeros contribute plus or minus 20 dB per deck, it's real easy to just draw a line from here to there, or do 20 dB per deck, because that would be like right here going straight across. Okay, so now, what we have to do in order to get the magnitude plot, all the points for it, you can kind of draw the effects of each pole and then add them up graphically, but that can be a little bit inaccurate. So what we're going to go ahead and do is set up a table here. Make sure I've got all my stuff lined up correctly. Okay, so we've got a pole at 0, pole at -1, and then -2, and then a 0 at -3. Pole at -3. Okay, we'll go ahead and line those up like that, like that, like that, like that. Okay. So, what we're basically going to do, if you have a pole at 0, you don't really consider it 0, you just consider it as a small value, which is an odd thing about Bode plots, but it's just kind of the way it is. So our small value for this magnitude plot is going to be 0.1, just because that's the typical thing that's used again. Or, that's That's how my professor explains it. So for the pole, for the start at 0.1, you're going to basically, the top value is going to be the positive numerical values of each one of the poles, or each one of the values from the transfer function, pole or 0. So the 0 pole is going to be 0.1, the pole equal to 1 is going to be 1, and then 2 is equal to 2, and then 3 is for the 0. So you just do it in this order because as you make the graph, you're able to add and subtract things as they go. Okay, so with the pole at 0, it immediately contributes a negative slope of 20 dB per deck, so negative 20 dB per deck. None of the other parts of the transfer function contribute any angle, really, at this point. Okay, so then, when you get to 1, well then this second pole at 1, or it's at negative 1, technically, but when you're drawing Bode plots, you consider the poles as the positive values when you're drawing the Bode plot. You don't really go, oh, it's a negative 1 pole. You take this value right there when you're drawing it up. Okay, so then this is still having an effect because poles in the magnitude plot, poles and zeros, they contribute that slant forever, basically, that angle forever. But then this pole is having an effect, so we have a 0, and then we go 0, this has 0. I'm actually going to add another row, total. This is going to be negative 20 total angle, and then negative 40. And then we go to 2 now. So we've got negative 20 still acting, negative 20 from the first pole still acting, negative 20 from the second pole still acting. And then, well, this one has just shown up, I apologize. So we just hit negative 2 on the plot basically, so it's going to start contributing negative 20. Okay, and then this still has nothing, and then you have the pole, negative 20, still contributing negative 20, still contributing negative 20. A 0 contributes positive 20, plus 20, so you've got 60, and then negative 40. Negative 60, and then negative 40. So that's the slant, the angle of the magnitude plot as you go along. Now, that's the basic sections of the plot between each one of the values of these poles. So we can say, okay, well, I've got a pole at 1, 2, and a 0 at 3, basically. So these are the rows where everything is going to work. But since we have this phase shift right here, it's not just drawing it all out. You actually have to find the values where they are because of that gain that's associated with this function. So in order to do that, you set up another table. It's going to be frequency, I'm going to abbreviate it as which is radius per second, and then magnitude, the actual magnitude that we have. Okay, so starting out with this, at 0.1, which is the pole of 0, we know that we immediately have a gain of 23.5. And that's because of this calculation that we did earlier up here. When S is really small, or basically 0, you have a unitless value of 15 that you turn into a dB magnitude of 23.25 or 22. It depends on how you do the calculations. This is how the solution is going. This is the value that was calculated. Okay, so there you immediately start the Bode plot right here at 23, basically. Then you go on to the next polar 0, which is 1. And the way you do it is you take the previous magnitude, 23.5, minus the angle that the plot is traveling at. And in order to show this, well, we're working at 1. It's going at negative 20 dB per deck, and it's going to go on like that forever. So you can basically put a point right here and go negative 20 dB per deck, right there. So we're traveling at negative 20 dB per deck. So you take the original value of the magnitude minus 20 dB per deck, minus 20 dB per deck, times log 10 of 1, which is the value that you're just hitting on right here, this full value, divided by 0.1, which is the value that you just came from, basically. And if you calculate that out, that is equal to 3.5. Which makes sense because you were at the value of 23 magnitude and you were coming down at negative 23 dB per deck. You were able to travel a full decade, so it makes sense that you just lost 20, which leaves you with 3.5. So not too bad right there. But now as you get into smaller sections, you move on to the second pole, and go from 3.5. This one just contributed -20 up here because you're traveling at -40. A slant of -40, so you go 3.5 minus 40, which is this, because we're working with going towards the value of 2. And you can see that because it's a little bit off because this is the row for 1, but row 1 just contributed -40. So what you would like to do is put something down there kind of, and you can draw your line, oh well, I'm going this way at -40. This way at -40, so right along that line. So you've increased the slant going towards 2. So minus 40 times log 10 of the value you're going to all over the value you're coming from. And if you calculate that out, you'll end up with -8.54. So if you look at that, and this is like 20, and we're on the value of 2, this is 20, 2, 8 is going to be somewhere right about there. So at a slant of -45, basically. Okay? So now, you're at 2, it contributes another -20, so now you're moving down at -60, which is an even greater slant than what your previous one was. And you just go through the process again. 3, -8.54, minus 60 now, from here, times log 10 of 3 over 2, where you're going, where you're coming from, which is equal to -19.1 dB. These are all in dB. And that's what this conversion is for, turning the unitless value into a dB. Okay, so you're at -20 now. This is at 2. This is 3. Basically, I'm going to say basically 20. And it's really tough to see here because it's such a small division, but you really do have a slant increase again right there. So this is at -20 dB per deck. This is at -40 dB per deck, and this is -60 dB per deck. And now, that's going to continue on basically until you hit 100. Wait a second. Make sure I get this right. I don't want to mess you up. Is there original code for something? Yes. Okay. -60. Okay. 3, -60. Okay, but here at -60, this is the value of the 0, and I'm sorry. Now you were traveling at -60 dB per deck, but now since that 0 has shown up, you add on 40 from this up here, right here, and you find, and since the magnitude plot, the sum of the angles, the slants basically add up and continue on for infinity. This is going to continue on at -40 dB per deck, as we said before, and since there's no in value for that, it doesn't really matter. I mean, what you could do is you could say, like, put in some random frequency so you have a point to draw to, but quite honestly, if you're just kind of drawing out the Bode plot, you can say, well, I'm at -20 right here, well, that's 20 dB per deck, I'm moving at 40 dB per deck, so you can draw a point like right about there, and finish it out. So now you're moving at -40 dB per deck. And that is your magnitude plot, and that goes clear on out to infinity, basically, at that angle. So you go at -20, -40, -60. The main thing is really, in this table, just making sure you keep these slopes aligned with where you're going. So you can draw the picture first, kind of-ish, and then refine it with these values, and the picture will keep you straight in doing this part. Or if you're good at this part, just go ahead and crank right through it. It's usually not too bad. If we did not have a pole at 0, what you would have seen is the magnitude plot would have started at 0, gone horizontal until it hit 1, and then it would have hit the -20 caused by the pole at this point. But since we have a pole at the origin, you have this gain. That's where that comes from. Okay, so that's the part, the magnitude plot, but now we have to do the frequency plot, which is a whole other set of tables and charts. Okay. So, with the magnitude plot, I want to go back up here to with the phase plot, the phase plot, I apologize. We know that it's going to end at -80, and since we have a pole at the origin, it's going to start at negative 90. And that's just a given again, because since this pole is at the origin, and every pole contributes negative 90 degrees over 2 decades, the pole at the origin doesn't really have 2 decades, so you just automatically add negative 90 to the phase. So I'm going to go ahead, let me double check my picture here. I'm going to go ahead and put 0 up here on my phase plot. And I'm going to put negative 90 right here, and then negative 45. Then we'll go negative 135, negative 180, just like that. And I'm doing 45, you want to kind of split these up in 45 because zeros and poles contribute negative 45 degrees dB per deck over 2 decades, so that's a good kind of scale to use. And in order to make sure it aligns with the magnitude plot, because you need these for phase and gain margins, make sure that these rows are the same. I'm using different notations on the axes, 0.1 or 10 to the minus 1, whichever one you use. Hopefully you're familiar with both of them. Just a good thing to see. Okay, so now, for the frequency then, cover all that up, start fresh. What you do is you don't even need that. You don't need the gain margin or anything like that. That is giving you where it starts. This gives you where it ends, so you kind of have a basic layout of where you need to end up with everything. So then, what you do is you go ahead and lay out your poles. Well, you've got a pole at negative 1, and then a pole at negative 2, then a 0 at 3, negative 3. You'll notice that I'm not using the pole at negative at 0. That's because we already accounted for it. It basically disappears after you say, okay, well, I start at negative 90. So we're starting at negative 90, bam, that pole's taken care of. And it has no effect after that. It doesn't cause an angle or anything else. If you didn't have these other things and you had a pole at 0, it would start at negative 90 and then just go horizontal. Okay, and then the total. Set this up like this. It's kind of a rough chart. I apologize for that, but you'll see how it works just as well. Okay, now, since poles and zeros contribute 90 degrees over 2 decades, what you do in creating the angles, the sum of the angles on any given point of the chart, is you take a decade below the polar 0 and a decade above the polar 0. And the way this looks is for like this pole at 1, you go 0.1, and then you go for this pole at 2, keeping it in order, you go 0.2, and then you've got a 0.3, 0.3, and then 0, you can pick 0 just because it's kind of handy and it's there. And then you've got, or no, this is 10, I apologize, 10, which is the other side of 1, and then you've got 20, and then you've got 30. So, looking at this plot, okay, so you've got a pole or 0 at 1, a decade below is 0.1, a decade above is 10. So that's how that works. Okay, so you set up those values, which is the range that each one of these has an effect. Okay, so at 1, the pole at 1 or negative 1, you've got, it creates an action of 45 degrees per decade. Okay, and then over here, you're moving along, another pole shows up, so it adds another 45 degrees per decade. So our total now is negative 45 and then negative 90. This is the effect, the slant that it's having on the chart. And then you have a 0, which goes to negative 45. Oops, sorry. This is negative 45. Add that in right there. That's why it's negative. I apologize. And then you got negative 45, and then you have a plus 45 because a 0 has a positive 45 degrees per decade. Okay, then you get to 10. Well, at 10, this 0 has used up its effectiveness, basically, so it fizzles out to 0. If you can think about poles, they go down, they create an angle for 2 decades, and then they level back out again. So this would be like the effect of one single pole creating the negative 45 degree slant, and then losing it and going back to normal, basically. Okay, so that's negative, and then you've got 45. And plus 45, because these are still both acting, which ends up with a total of 0, and this is a total of negative 45. And then right here, you get to 20. 20 is the last part of the effect of this pole of 2, the pole of 2. So it goes to 0 at 20. And then you just have plus 45, and this is 0, or plus 45. And then at 30, the effect of the 0 has worn off because we went from 0.3 to 30. So you got 0, 0, 0, slope is 0 again. Okay, so if you want to kind of look at that, well, we're starting at 90. We're starting at 90, we go along. Oh, excuse me. Starting at 90, it induces a negative 45 degree. We're at point 1. At point 1, we have the effect of the first pole, which is negative 45 degrees, which is going to go along until we get to point 2, which adds on another 45, and then point 3, which adds a 45, which levels it out a little more, and then so on and so forth. And you'll see that how I draw it. But in order to do this very effectively, you really need to figure out what the values are so you can draw the points to figure it out. Okay, so for that, we create another table, just like the last one for the magnitude. And the phase now in degrees, just like this. Frequency in degrees, you go 0.1, 0.2, 0.3, 10, 20, 30, and then to finish off the plot, basically, you can put in 100 if you want to. This isn't really necessary, but it's something you can do. Okay, so at point 01, the phase we know is negative 90, because of basically the pole before this, which is the pole at the origin, which would put the phase at negative 90. But then, so we have a pole here, which is going to induce a negative 45 degree angle going from point 1 to point 2. So at point 2, you have the value, the original value up here, minus 45, which is the slope going from this point to this point. 45 log 10 of the pole that we're going to, point 2, all over point 1, which is where we're coming from, which is going to equal negative 103.5 degrees. So if you look at our frequency plot, if we're looking at, this is 0.01, this is 0.2, 0.3. At 0.2, we're looking at negative 103, which is going to be somewhere right about there, which is at an angle of negative 45 dB per deck, just like that. Sorry, I'm not using my ruler, but it's too small of a section. Okay, so now going on to point 3, we have a value of negative 103, negative 103. Going from 2 to 3, we have a slope of negative 90, minus 90, log 10 of where we're coming from, point 2, and this will give you negative 119.4. And again, this is just a conversion factor into degrees, basically. Just like the last one was a conversion factor into dB. Okay, so negative 90, so at point 3, or negative 120, well, this one was 103, so this one's going to be right about there. Which is, it's tough to tell, but that's a higher slope. This is negative 45, this is negative 90 degrees per deck. Okay, so now we're at 10. We go to negative, where we came from, 0.4, the previous phase, minus 45, because going from 0.3 to 10, we have a slant of negative 45 degrees. Log 10 of 10 over 0.3, where we're coming from, which is going to equal negative 187.9. Okay. So now, I'm going to crank through the rest of these pretty fast. So negative 187.9 plus 0, 10 to 20, 0. Plus 0, log 10, junk, so on and so forth. That's all going to go to 0 because of that 0. Negative 187.9. And then for 30, we got negative 187.9 plus 45. Log 10 of 30 over 20, which is equal to negative 180. Remember at the beginning, we predicted the phase because we have 0 and 3 poles, the phase is going to be negative 180 because the poles, you end up with a net of 2 poles, which each contribute negative 90, which put us at negative 180. And there we are, lo and behold, at 180. And this 100 frequency is not really important. You could stop right there and just say, okay, well, everything goes on from there, but this is just a nice way to kind of finish out the graph. Negative 180 minus 0, or plus 0, because there's no slope going on from there, is equal to negative 180. Which is this slope right here. So you can put like 100 out here as a check to finish everything off, and everything's still 0, so 0 to 0. Okay, and if you draw that all out, at point 2, and then at 10, let me get this arranged. At 10, we've got negative 187, which is somewhere right about there-ish. And then we go along to 20, which is right about there-ish. And then at 30, 10, 20, 30. You come back up to negative 180, and then out here at 100, you're still at 180. So connecting those dots, you got that, and then going on out there and hell forever. And that's what your Bode plot looks like. And if you wanted to like smooth it out or something, this is your asymptotic estimation. The real Bode plot would be something like this, maybe with a little hump in it, but not much of one. And you just kind of round out all the corners, basically. So there you go. From a transfer function, we were able to create the magnitude and phase Bode plot. You just create a table for the poles and figure out what the slant basically is, the slope of the graph. And then you figure out what the points are by using this equation, which is basically y equals mx plus b, really, because this is where it's crossing the line. This would be b, this is the slope, negative 45, and this is the x. So that's how you take a transfer function and turn it into a Bode plot.